Hello, this is Zhiyuan Mao from Purdue University. Today I'm representing my co-authors to present our work, Single-Frame Atmospheric Turbulence Mitigation, a benchmark study and a new physics-inspired transformer model. Atmospheric turbulence effect occurs when one tries to take high-resolution images or videos over a long distance. This video, called the chimney, is a widely used benchmark data for evaluating atmospheric turbulence mitigation algorithms. It can be seen that the major degradation types of atmospheric turbulence include random geometric distortion and spatially and temporally varying blur. These degradations become stronger with increasing temperature and imaging distance. Besides the turbulence effect, due to the difficulties in long-range photography, the images can often have visible noise, motion blur, and defocus blur. So why should we care about turbulence? Besides the clear intention that we want to have better photographs, the atmospheric turbulence will also severely impact the performance of long-range computer vision systems. This is because the turbulence effect will both reduce the visibilities and randomly change the shapes of the objects. Such randomness of atmospheric turbulence will also cause the visual recognition system to produce inconsistent predictions across different frames. Atmospheric turbulence mitigation algorithms are here to help. Imaging through turbulence has been studied for decades. The conventional optimization-based methods often adopt a multi-step pipeline to remove different types of degradations. These methods are computationally expensive, but they can be applied to any general scene restoration. Recent deep learning-based methods are often more efficient and can achieve better performance. However, their performance often suffers when the testing data is beyond the distribution of the training data. It is also very costly and difficult to collect data with enough variety to train these networks. In addition, the testing data are also scarce. There isn't a widely used benchmark dataset. In this paper, we have two main contributions. On the algorithm side, we propose the TurbNet, a new restoration model for single-frame turbulence mitigation that achieves state-of-the-art performance. On the benchmark side, we present two new datasets with real atmospheric turbulence for evaluation purpose. We first look at our restoration model. We recognize that the conventional CNNs have two shortcomings that make them unideal for turbulence mitigation tasks. Their local receptive fields are unable to capture the global Lucke effect. The static convolutional kernels are not designed to handle the highly spatial and temporal dynamic turbulence. We use the transformer-based backbone for feature extraction since it doesn't have the above constraints. After obtaining the image features, we jointly reconstruct a clean image and estimate a turbulence distortion map. By redegrading the restoration output, we form a self-supervision loss to facilitate the unsupervised fine-tuning on real datasets. Now we present our new dataset. The first dataset is called the turbulence text dataset. This dataset is collected over a truly long distance. Since no ground truth is available, we use the accuracy of text recognition systems as the performance indicator. The second dataset is called the heat chamber dataset. The turbulence in this dataset is synthesized by artificially heat up the air along the imaging path. Ground truth images can be obtained by shutting down the heat source. Since we now have the access to the ground truth, any conventional full reference metrics, such as the PSNR and SSIM, can be used here for evaluation purpose. In the end, we showcase some of our results. In the upper set of images, we demonstrate the effectiveness of the TurbNet and the turbulence distortion map. It can be seen that, with the assist of the turbulence map, TurbNet can faithfully restore the turbulence degraded images. We also show a qualitative comparison against several turbulence mitigation algorithms and general restoration methods. All of the methods are trained using the same datasets. Our TurbNet achieves the best overall performance. We then show some quantitative comparison on the heat chamber dataset and the turbulence text dataset. It can be seen that the proposed TurbNet consistently outperforms other methods. Please refer to the paper for detailed definitions of the metrics. That's all for this presentation. You're welcome to download and try our code and datasets. Thank you.